Okay, in this video, we're going to be talking about inverses of matrices. We're not going to go so much into actual example problems, so this video is going to be more on the theory side. Okay, in the next video, we'll talk about actual applications of how to find the inverses, especially using the Gauss-Jordan elimination method. So let's start off with, well, what's an inverse of a matrix, and why do we need it or care about it, right? That's why we're learning it. We're learning it for a reason. Well, let's go back a bit. Let's go back to maybe 2 years ago when we learned algebra. So, do you remember what a reciprocal is? Right? If you don't remember what a reciprocal is, let's go through it real quick. So, let's say I have a number. Let's call it 8. Right? That's just a regular number. Now, let's say I ask you, what is the reciprocal of 8? Well, the reciprocal is just uh, you take the number and you flip it, right? So we flip 8. So instead of 8 being on the numerator, we could rewrite this 8 over 1. The reciprocal becomes 1 over 8. It's as easy as that. We take it and then we flip it around. With that being said, the inverse matrix is the reciprocal of a given square matrix or a given n by n matrix. That still doesn't help us understand why we care about inverse matrices, right? So I'll bring it back home. So let's think about why we used reciprocal in the first place. Back in algebra, we used reciprocals to handle division of fractions over a fraction, right? Or any number divided by a fraction. We had to take the denominator and then flip it, multiply it, and then boom, there we go. Well, here's the interesting thing about matrices. Well, matrices have no division when it comes to manipulation. So we have addition, we have subtraction, we could even multiply matrices given certain conditions, but there is no concept of division. Hence, we have to deal with the inverse of a matrix in order to essentially get the reciprocal of a matrix such that we could do a quote unquote division operation. Because the inverse of a matrix is essentially the reciprocal, we have this important relation that we could put in our tool belt or toolkit. Okay. So if you remember when we're dealing with reciprocals and we multiply the original number with the reciprocal, we get what? We get a unit value, right? For example, let's go back to the example above. Let me switch colors into yellow. Let me draw an arrow here. For instance, let's multiply the original number 8 times 1/8. What does that give us? Well, the 8s cross cancel, or not cross cancel, they cancel each other out, or they simplify each other in a way, and you're left with 1. Well, that's very important for us when we're dealing with inverse of matrices because we have a similar relation. Let's assume we're given a matrix A. A is an n by n matrix, and A raised to, let's call negative power 1, which, as you should know by now, if we use this for a scalar number, that's just the reciprocal, right? This is an n by n inverse matrix of matrix A. Okay? So, now that we have that out of the way, we have this relation of matrix A times the inverse matrix of A. It is the same thing as if you did the inverse matrix of A times the actual matrix A. That will give you this n by n matrix, which we call the identity matrix. And we denote that with a capital I. So I here is an n by n identity matrix. Now, for those of you that are not familiar with an identity matrix, especially if this is a new topic for you, Well, it's a fancy way of saying, hey, you have an n by n matrix with all the diagonal components having a value of 1, and all the other components of that matrix is 0. For instance, if we're dealing with e.g., if I is, let's say, 3 by 3, that means the identity matrix for this 3 by 3 is 1, 0, 0, 0, 1, 0, 0, 0, 1. Notice how all the diagonal components, like I mentioned earlier, are 1, right? That's all there is to it. That's all what an identity matrix is. So bringing it back to the beginning of this part, when we multiply, it doesn't matter for this, in this case, the order. If we multiply the inverse matrix with the original matrix, we will get the identity matrix, which goes back to the reciprocal analogy, right? The original number times its reciprocal gives us 1. And this is important to know because let's say you're given a problem of 2 different matrices, but the same size. So let's say a 3 by 3 is one matrix, and another matrix is another 3 by 3. And your goal is to determine, are these 2 matrices inverses of each other? You might be scratching your head and be perplexed and say, well, I don't want to have to compute the inverse of one of the matrices to determine if they're inverses of one another. You don't have to. At that point, you have the 2 matrices. All you have to do is multiply them together. And if you multiply them together and it yields an identity matrix, then you can conclude that the 2 matrices are inverses of one another. So let's move on and ask the question, are all matrices invertible? The simple answer to that is no. Only square matrices have an inverse, for the most part. Later on in higher levels of math, maybe even in, I believe, linear algebra, you'll learn that there are a few exceptions where you could find a quote-unquote inverse for non-square matrices. But for this video's purposes, we're just going to say only square matrices are able to have inverses. But that doesn't mean that all square matrices will have an inverse. Okay? Think about that real quick. That might be a little bit confusing at first. So only square matrices have the potential to have an inverse. But that does not mean that all square matrices have an inverse. Once you have that unwrapped in your head and you understand that, you might be asking yourself, okay, well, how do we determine if a matrix is invertible or not, or if it has an inverse? Well, this goes back to the discussion of discriminants, right? Remember how in the discriminant video I mentioned that we use the discriminant for 2 main purposes: to determine if a system of equations is solvable, and 2, if the determinant is able to help us distinguish if a matrix has an inverse or if a matrix is invertible. So one way that you could think about it is go back to algebra and remember the concept and idea of a discriminant, where it helps you determine how many real solutions there are with the quadratic equation, with the quadratic equation that you're dealing with, right? The discriminant is, I'm going to call it D, is b squared minus 4ac. Now, if D is equal to 0, that means one real solution, SLN. If D is greater than 0, that means you have 2 real solutions. And if D is less than 0, then you have 0 real solutions, right? So